Here we go. The first of the last. This will be the first topic for our last section of Calculus 1. Is the home stretch. So optimization is going to be our word problem. It's actually going to go with what we're tested on. Maxes and mins. We're going to optimize something, right? Finding the greatest, finding the least. Optimize. Maybe you want the least amount of pollution. You want to optimize your plant. There's just so many applications to optimization. It's ridiculous. Just start thinking about things that you want to optimize or have the greatest or the most or the least of them. I mean, it just goes on and on and on and on. So let's just dive right into it. These are the word problems. These are the applications. What you were just tested on. Now we're going to see, do you know what's up? You're going to use those same concepts and just throw them towards real world situations. Not about real world. Some bullshit shapes and stuff, but we'll do some real world. We'll get into it. So let's talk about how we're going to solve these word problems. Now, in any freaking word problem, dude, even if you're a shit drawer like myself, draw a picture, draw a sketch, draw something. You know what I mean? Just try and get it down. If you don't know what the hell's going on, you haven't drawn a picture, you're not trying. I mean, you just draw something. Yeah. So, draw a sketch trying to figure out what the heck the person is trying to say to you. And now the second one's the most convoluted wording. I don't know why it's written like this. I don't know why I have it, but it's correct. So we want to find an expression for the quantity to be maximized or minimized, and the constraints on the variable, which is basically just saying this. We need to find an equation and a constraint. And I'll talk more on that in a second, okay? You're going to find two different things. You're going to find something that you want to maximize, some sort of equation you want to maximize, like maybe the area is equal to the length times the width or something like this, and you want to maximize the area, so you want to do stuff to that equation. But maybe you got some constraint. Maybe the length is bigger than the width by this much, and that would be the constraint. So you get two equations, shit you can plug in. So let's see what's going on here. We'll keep going, because I could talk all day about this until you see a problem. It's not going to make much sense. And then possibly we use the substitution method to create a single equation. We typically do this in almost every single problem. It's kind of a game. And then the last thing, and then, hey, 4. This should be pretty freaking familiar. Take a derivative, set it equal to 0, and solve for that value of x. Right? Because that's where we're going to find. Come on, dude. Know what I mean? Maybe that's your graph, and you're like, I want to know where the most is. I wonder where that could possibly be. Well, that's where the derivative equals 0, right? You get those peaks and those valleys. Maybe it's at this time right there, time 1. Maybe that time, or I don't know. It doesn't even need to be a time. All right, cool. And then 5, we have this thing. It's pretty much optional. You can take a second derivative, would tell you whether it's a max or a min. Sometimes it's just blatantly obvious. I'll make fun of some of the problems as we go through to show, like, do you really need to hit it with the second derivative to figure out whether 0 or 7 is going to be your max or your min? We'll continue on. And then 6, you want to plug it back in. You got to answer the damn question. So actually, be real careful with how you answer your questions. You got to answer what they're saying. And sometimes I miss them too. So let's just jump into a problem. And here's our first one. A farmer has 360 feet of fencing and wants to fence off a rectangular field that borders her barn. Therefore, she needs no fencing along the barn. What are the dimensions of the field that yield the largest area? Let's do step 1 right off the bat. Let's just get a dang picture. There's a farmer trying to put a fence along her barn. Can you catch that? First sentence is just talking about that. All right, let's draw a picture. And you're gonna here's my. Oh, I don't want that color. I want this color. All right. There is my barn, and you have to have a little bit of like suspension of disbelief when I draw, right? Because I'm a shit drawer. All right, and now she wants to put a barn. Or she wants to put a barn. Shit. She wants to put a fence, a rectangular, right? A rectangular field, a fence off a rectangular field that borders the barn. So she needs no fencing along the barn, right? So we just need to draw ourselves a little barn, or not a barn. Why do I keep saying that? I'm not redoing this damn thing. We're keeping going. So maybe something like this. So a little area inside of here, a little something. Cool. We drew a freaking picture. Now we kind of know what the hell's going on. It's a rectangle with only 3 sides. Dope. But, all right, now, what's in blue there? That's all the fencing. And the sentence says, what? A farmer has 360 feet of fencing. Oh, so that what's in blue? Well, shit, that has to be 360. So I'm just going to kind of draw this off to the side. In blue. That length was 360 feet. All right, that's the same thing as right here. I just kind of straightened it all out, like it was just linear feet not going around. Cool. All right, neat. Moving on, just trying to make heads or tails of this problem. So a farmer has 360 feet of fencing. Okay, we got that down the length, and wants to fence off a rectangular field that borders her barn. We got that written down. Okay, cool. Therefore, she needs some fencing along the barn. All right, now what's the question asking? It's asking us, what are the dimensions? So here's the questions. What are the dimensions, all right, of the field that yield the largest area? All right. So the field, we want the largest area inside of it. I think that's what it's trying to say. So we did step one. Now what's step two? Let's go back up and take a quick look. What's step two? We want to find an expression for the quantity to be maximized or minimized and the constraints. Oh, we need to find that equation. Look, I kind of already wrote it up there. It's like I knew what we were going to do. The area is equal to length times width. And then we have a constraint. Like, you only have 360 feet of fence? Oh, shit, we just need those two things. Let's go back to our problem. All right. What do we got here? So we want to find it. So let's write it down. What's our equation? Our equation is talking about what are the dimensions of the field that yield the largest area. Oh, we need the area formula. But in order for us to do the area, we gotta label our picture. Do you want to call it length and width, or do you just want to call it X and Y? We could call it length and width. Do you want to? Nah, I don't want to. I'm just gonna call it X. And those are both the same because it's a freaking rectangle, right? And then Y. Well, let's go. Plugging this thing right in. The area is going to be what? The width times the length, X times Y. Awesome. So that's our equation. That's that equation I was talking about. Now we also got to get one more thing. So this isn't our step two. We want to get one more thing. We got to get that constraint. And actually, I'm going to use a different color for the constraint. Let's change that color. Let's use something different. And let's call the constraint. So we need this. We got 360 feet. Remember this thing right back up here? Actually, let me just do it in blue. That'll make more sense. That's 360 feet. So isn't that we take our x plus y from right down here, huh? We add those things up. That's called the perimeter. And wouldn't that have to equal 360 feet? So maybe if we turn this thing around, we could just say 2x plus y is equal to 360. There we go. There's our constraint. So we wanted these two things here. We wanted to get our area, or we wanted to get an equation to be maximized, and then we needed the constraint as to how much it could be. All right, now let's just jump back. So once we have this, now what's our next step? It says to possibly use the substitution method to create a single equation. And that's what we're going to do next. It was like back before, we don't want to be doing any sort of product rules or anything crazy. Like, we're pretty much done. We're like, no. Why don't we go down here, take this bad boy, solve for y, and then plug it in right there. Yeah, I think that might be a good plan. So let's solve for y. So we're just going to subtract that thing over and say y is equal to 360 minus 2x. Cool. So here comes our little sub here. Our next step. We're going to take this, right? We're just going to pop it into our equation. And this is the game each time. You're going to want to pop that thing into the area is equal to x times, and then we just go plug in, and there's that 360 minus 2x. All right, we're getting it into one variable. I'm telling you, you want this shit in one variable. You do not want this in a bunch of different variables if you can help it. Well, there we go. The area is equal to 360 times the width minus 2 times the width squared. There we go. There was step 3. Now what's step 4? Take a derivative, set that bad boy equal to 0, and let's go figure out where that max lies. What's the width? That's going to make this. So step 4. Let's go take that derivative, huh? Let's go take a derivative. So we're going to say that the change in A, or however you want to write it, I'm just going to call it dA dt. We're going to set that thing equal to 0 anyway, right? So we're going to get 360 minus, what's that going to be? 4x. Minus 4x. Oh, and we're going to set that thing equal to 0 and solve, right? So here we go. We just pop it up. Nope, this is still in our fourth step. We're going to set it equal to 0. That looks like shit. I'm going to change it. So setting it equal to 0, or 360 minus 4x. Let's do a little bit of frickin' algebra. You get 4x is equal to 360. Come on, dude. What do you think? 180, what is that, 90? X is equal to 90? Well, duh. Once you get this, well, it says that we can now take a second derivative to figure out if that's going to be a maximum or a minimum. Do you want me to tell you how to make a minimum frickin' area on that thing? Let me show you. Minimum area. The width, x is equal to 0. That's the minimum. That'd be no area. So I highly doubt that we found a minimum here. I'm pretty sure we found the damn maximum. If you want to plug it in and do part 5, you go right ahead. Number 6 says plug it back in and go find your dang answer. And where you're going to find that, where you're always going to take your answer from here, is you want to plug that thing right back into here. Whatever your substitution was, whatever we did from step 3 to plug that bad boy in, that's what we're going to plug. We're going to want to take it and put it back into our equation for step 6, which says that y is equal to 360 minus 2 times that x we found right above up here. So we're going to take that, find out that our y is equal to 360 minus 180, which y is equal to 180. Therefore, the barn would need to be 90 by 180. And this is feet. Yeah, buddy? Got it? That's the first one. This is a little classic against the barn. We did it. We got it. There's our solution. More to come. See ya.